This video will help you realize if you need the Annulus feature in DFTFringe or not, what's the point of annular polynomials, and how to use the feature in DFTFringe. If I go too fast, then pause. If I go too slow, then speed it up. This video has 3 sections. Do you need Annulus I-grams? Most people don't need it. One reason you need it to use it is if your mirror is perforated, if it has a hole, and the perforation diameter is more than about 30% of the mirror diameter. If that's your mirror, then you definitely need this feature. Another reason is that you may have a secondary that blocks a lot of the primary mirror, such as that the center of the mirror doesn't matter much, and you want to know how good the mirror is if you ignore the center. Again, if this is more than 30%, you should use annular Zernikeys. If it's less than 30%, you can just use the inner outline feature. Keep in mind that even if your secondary is, say, 30 millimeters in radius, you may care about parts of the mirror less than 30 millimeters from the center because for stars at the edge of the field of view in a 4-degree field of view, those stars are 2 degrees off axis, so you will be using parts of the center of the mirror for those stars. Why using annular polynomials is important. You don't need to know why these are important, so if you don't care, then skip to the next section, how to use the feature in DFTFringe. The quickest answer is that DFTFringe uses a matrix function called solve that finds the least squares best fit Zernike polynomials, and the solve function requires the polynomials to be orthogonal. As the hole grows in a mirror, the circular Zernike polynomials get less orthogonal, and so the solve function returns less and less accurate values. This messes up the defocus term because we subtract off the defocus based on this term multiplied by the defocus shape. We don't care if the wavefront has defocus, as that just means you didn't place the bath perfectly at the center of curvature. If you subtract off the wrong defocus, you are left with a wavefront that still has some defocus, which will look like error, and it will show up as error in the Strail and RMS values. This also messes up the spherical aberration term, which means the mirror may be more corrected or less corrected than is shown in DFTFringe, where it shows best fit conic. That's the quick answer. Here's a longer answer. As an analogy, imagine you are trying to describe this red vector using unit vectors a and b, which are 1 unit long and orthogonal. Orthogonal vectors are perpendicular. You can easily see that this red vector is 2 units of a plus 1 unit of b. If you rotate b by 10 degrees to create unit vector c, you can now correctly say the red vector is 1.82 units of a and 1.02 units of c. But with these non-orthogonal vectors a and c, the solve function will incorrectly pick where the vectors pass closest to our red vector. So 2 units of a and 1.31 units of c. That gives us the wrong breakdown. Both values are wrong. Vector c has some a in it. Now back to Zernike shapes. Now instead of using just 2 multipliers for a and b, we use typically 49 multipliers /scalar /terms, and instead of representing just a vector, we represent an entire surface shape. So we have 49 Zernike shapes and solve for the 49 terms. Here's the surface shape for defocus and spherical aberration. It's not obvious, but the Zernike shapes are all orthogonal. Changing one doesn't affect the others, just like changing vector A doesn't affect vector B in our analogy. Here is a cross-sectional graph of defocus and spherical aberration where the left edge is the center of the mirror and the right edge is the outer edge of the mirror. The orange curves are the curves we use for normal circular Zernikes, and the blue curves are specially designed for annular wavefronts. At 10% annulus, there isn't much difference. By 30%, they simply seem scaled a little different, but the shapes are different also. Here's 50%. Let's look at 80% for a bit. The orange curves, the circular Zernike curves for defocus and spherical aberration, are looking very similar. It's easy to see that they are not orthogonal. Changing the wavefront only by the orange defocus curve will significantly change the orange spherical aberration curve. They are not even close to orthogonal. They actually started being non-orthogonal even with just a 10% annulus, But when analyzing a wavefront from a mirror, you are typically going to get errors less than 1/100th wave even with a 30% annulus using the circular Zernike polynomials. Another takeaway. Looking at, say, the 50% annulus spherical aberration, you can see that because the annular SA, the blue curve, is more extreme, the Zernike terms will be smaller. So the null has to be correspondingly smaller because in the end we are talking about the exact same parabolic mirror. It's just that the middle of the mirror is missing. So it's the same null curve, but the null value is scaled differently. If you are in DFTFringe and check and uncheck the annulus box, you will see that the null changes to a smaller value for the annulus. I just spent maybe 3 minutes explaining what probably requires many hours of thought, but if you rewatch this section 10 or 20 times and really think about it, I think you'll understand. It took me probably 20 hours and several emails with Michael Peck before I finally understood. Feel free to email me with questions, and that might lead to me editing this video to make things clearer. How to use annular Zernikes in DFTFringe. Let's start with mirror configuration. You'll want to check the annulus box and enter something for the center diameter or percent. If you fill in percentage, it calculates the hole diameter. If you enter hole diameter, it calculates the percentage. You can use millimeters or inches. Unlike the outer mirror diameter, you don't have to get this perfect, and I recommend you pick something a bit smaller than the actual center diameter. That way, you can get data right up to the edge of the hole, because any fringe information inside this inner diameter will be discarded during processing. If you are processing multiple I-grams, you should use the same annulus size for all of them to avoid confusion with varying nulls. You can see that if I change the percentage, it changes the null amount. Things will work fine if you average wavefronts with varying nulls, but it will be more confusing. You may wonder about this obstruction parameter here. It's okay to set that to the same as your annulus diameter, but you don't need to. The intention of this feature is to mask out the center of your mirror if you don't want to include that portion in the error calculations. But it doesn't do as good a job as the annular feature. If you only use the obscure feature, the inner area is still used to calculate and remove defocus and to calculate best fit conic, so massive errors in the center could influence those. If instead you use the inner outline feature, also known as central hole, it will do a better job. And using annulus feature combined with the inner outline will do the best. By the way, when you are doing the central hole, there's this new button here. When you click it, it pulls in the annulus value. Again, you can see I set it a bit small on purpose as recommended. I also find the button is helpful when choosing my annulus size. One thing that hasn't changed is you want the central hole outline to be slightly bigger than the actual mirror hole in perforated mirrors, as you can see I did here before clicking the Done button. So that's it. Everything else is the same as circular I-grams. Note that it says annular here. Note that this null is meant only for this percentage annulus. Just like when analyzing circular mirrors, best fit conic will be -1 if your mirror is perfectly parabolized, -0.9 if it is only 90% parabolized, -1.1 if it is 10% over parabolized, and so on. Good luck, and check the comments section below because updated information along with people's questions and answers will probably end up down there.